what we use in our work. Then I will present the canonical model of convergent spacetime, and then just briefly the quantization that we did and the same classical approximation. And then we'll show the most interesting part, which are the results that we obtained, and then some conclusion. So let's start with time problem physics. So if you search for it, of course there are many ways in which people present this problem. But the basic idea is that in general relativity we have that this theory, so GR, is a diffeomorphism invariant theory. So this means that whatever coordinate we choose, the physics does not change. However, this is not true in quantum mechanics. So if we change our coordinates, in particular we are interested about time. So if we change, for example, time, we have that internal times variables are known to produce unitarily inequivalent quantum models. So we cannot do that without changing physics. So the problem of finding the correct interpretation of these non-equivalent models is commonly known as the problem of time. So usually there is no real way in which people introduce this problem or like how to solve this problem. However, there is a review by Isham, so the canonical quantum gravity of the problem of time. Okay, here. So it says, so the primary source of the problem of time in quantum gravity is the invariance of classical general relativity under the group diff n of diffeomorphisms of the space-time for manifold n, which is what I said before, basically. And then it says this stands against the simple Newtonian feature of fixed time parameter and tends to produce quantization schemes that apparently lack any fundamental notion of time at all. So what he does here, he presents 4 questions that should be answered in order to solve this problem. So I will show you that in our work we were able to solve, say, to answer 2 of these questions, and 2 of them we didn't touch on them, but they are really interesting, maybe in future works, or they are really interesting to be solved. So how should the notion of time be reintroduced into the quantum theory of gravity? So what we found is that the absence of time in a quantum theory might not be a problem after all, as any internal variable chosen in our theory will give the same prediction in the classical limit. So as I will show you in the results part of my talk, we see that the only discrepancy that we have when we change time at the quantum part is just at the in our case at the balance level, but at every classical limit we don't have discrepancy anymore. Then Isham posed another question, that is, so should attempts to identify time be made at the classical level, i.e. before quantization, or should the theory be quantized first? So as I say, there are 2 ways. So either we quantize first or we quantize later. But the problem still remains. So it's not really a problem this, because since we still have a problem, either we quantize before or later, the only thing that we can do is to use the easier approach. In our case, we chose to use the reduced phase-space quantization, and it means that we work with we choose an internal time variable at the classical level prior to quantization. But so that's how we work around this question. Then the 2 questions which are still remaining open are: can time still be regarded as a fundamental concept in a quantum theory of gravity, or is it status purely phenomenological? I think it's a really interesting and somewhat philosophical question that could be answered. And the other question is, how closely tied is the concept of time in the idea of probability? So we don't touch on these 2 questions, but I think that there are still interesting questions and should be answered in order to maybe solve this time problem if it's a problem at all. So, when I will discuss about clock during the presentation, the idea of a clock is basically, so how do we define time usually? We just have a system of reference. So for example, if I have 25 minutes for my talk, it means that we use the rotation of the Earth as a reference to define these 25 minutes. However, we could have chosen something else. So this is our clock, and what is represented here, so those 2 lines, for example, are 2 particles, and they are just evolving. And then we chose a 3rd particle, so this time t, as our clock. So we have these hypersurfaces, they are space-like hypersurfaces, and what we do is that each one of these hypersurfaces is at a fixed time. And we chose this time based on the evolution of this 3rd particle. Of course, if I say I change clock, I could have used, for example, the motion of this 2nd particle. So in this sense, this is what we mean by changing clock. So just changing the reference system to which we we consider our time variable. So, as I said, as we discussed in this previous slide, we have this foliation, and we will keep the ADN formulas and what follow. And just a brief overview of what the ADN formulas is. So basically, we foliate our space-time. So we divide it into this defoliation. So we have, again, space like hypersurfaces, and then they're at a fixed time. So for example, this will be t, this will be this t plus dt, and here we have time. So each of these foliation, each of this sheet will be at a fixed time. So then we have, of course, to know how can we go from one sheet to the other. So at the time, so if you want to know how the time varies from one to the other, we use what is called, we introduce the lapse function. And then if you want to know how the measure of sheet, if you want to know how the local coordinates are changing, so how can we go from one point to the other once we change our foliation, then we introduce what is called the sheet vectors. So it's important that those are not dynamical, those two quantities. And what we have is that another important thing is that the evolution from one sheet to the other estimates the action. And this is important because then we can actually obtain our equation of motion with these formulas. In particular, what we have is that the metric in the ADN formulas is given by this. And as you see, we have the lapse here, and then we have the shift, and this is just the spatial metric. And the Einstein-Hilbert action is defined in that way. And what we can do is we can actually write it as a function of the Hamiltonian. And then we have it, we introduce in this formulation, of course, we will have, as you can see from the metric, we will have then the present of the lapse and the shift. So there is no dynamics of these two quantities. So they play the role of Lagrange multipliers. Indeed, what we have is that the Hamiltonian, those are constraints in our theory. And why is it important? This is important because then we can introduce what they call the reduction formula. So what we have is that since we have this constraint, if we actually apply this constraint, which practically speaking means we can put it to 0, we have that our phase space is going to be, the dimension of our phase space is going to be reduced, and that's why the name, it's going to be reduced to a lower dimension. So then our work is going to be constricted in this surface, the constant surface. And usually, it also means that we have to fix some kind of gauge. So in this case, what we found is that if we have the Hamiltonian as a constraint, the gauge freedom usually related to this will be our time variable in this case. So to choose these time variables, we have of course to choose something that is varies monotonically, because we want our time to be either going forward or backward. So then we change, and of course it must be evolving, so we take some assumed Q0, for example, in this case, to vary monotonically with evolution generated by the constraint. So this is the allocation to choose our new time, and then we actually can define our dynamics to read such, where this is our chosen time. So we will call this Q0 as t because we know that this is time, and this is as it is usually called. And then what we can do is, since, as we said, we are still at classical level and we have this diffeomorphism invariance, we can actually change time. And we can choose our new time as t tilde. And this, of course, will be a function of our old canonical variables, so q and t, and our old time. So this will be our transformation, time transformation. But then what we have is that there must exist, of course, some variables which remains invariant under the transformation, because we know that this is the case, the physics does not change. And those, of course, are our observables. In particular, those are called Dirac observables, this di. And it means that what we have, and it's the key formula for all our work, is that these observables, they do not change after this transformation. And so we have this t is going to d, our t is going to d tilde, and then d is going to d, that is a function of q, p, and t. So of course, you could argue that this also should be d tilde. However, we can always find a way to define our Dirac observables such that it's in the same form as our previous t. So even though it's a function of this tilde variable, the form in which the observable is written is the same as the old one, just with different variables here. So now we construct our canonical model of primordial spacetime and we use perturbation. So we perturb our metric, so this is the usual form in which the metric is written here. So those are our perturbations. And then what we have is that we actually consider up to second order. And just for simplicity, our background is considered to be Friedman, so flat Friedman. And we consider field with radiation. So this is because it is not written here, but the form of the Hamiltonian, of course, is a function of W. And if you put W as 1/3, our computations are way simpler. So, but we can actually use other kinds of matter. So this is the total Hamiltonian, so is the sum of all the different perturbations. And remember that we are in a reduced phase space. So that's why you don't see the first order. So the zeroth order now is given by this formulation, and the second order is given by this, where the way in which we define this pi and mu, which are canonical conjugated, a canonical variable and pi is conjugated to mu, is just a scaling. So basically we define mu as a, so the scale factor h. So those are the modes, our gravitational waves, so our perturbed variables. And then, of course, a here and here too, those are is the scale factor, and the two dots indicates the derivatives with respect to conformal time. So I didn't say it before, but notice that here I wrote PA because usually we have PQ, those are our canonical variables, but in this case Q is our scale factor. That's why I was written PA. Okay, so now we have our Hamiltonian, and we know that there are these quantities, the observables, which are invariant under change of coordinates. And then what we can do now is, we know that those are constant of motion, so their total derivative is 0, but it means that we can written it in this way, where remember that we are now working in perturbation theory. So this means that our Poisson bracket will be a function of the canonical variables at the background level and at the first order. So this is the formulation, and this is equal to 0 because there are constant motion. What we can do now is, if we solve this equation, we will get two results, of course, one for the 0th order and one for the first order. So this is the solution for the 0th order, and this is the one for the first order. If you see, it's quite simple. But as I said, this formulation does not change if you now are working with mu tilde or pi tilde variables. So if we go to t tilde instead of working with t. Oh, okay, and W is just, if you see it here, because you could argue that there is no time dependence, but it's hidden in W, omega, sorry. So this is the way in which omega is defined, just to make the formula clearer. And of course, these observables, they form canonical pairs, both at 0th and first order. Okay, so now we have to change our clock. Before we define this clock changes t tilde, like a generic one, but now we have formulation because we want to see what is happening when we change this time. So we now do this change, so t is going to t tilde, which is defined as t plus delta. Delta is defined as a delay function, and it can be whatever you want as long as it satisfies these two properties. So first of all, of course, we want t tilde to still be a time. So this means that this time must either go forward again or backward. We don't want something strange going on here. So what it means is that when we do this change of variables, the Jacobian must be either positive or negative. And in this case, we chose it to be positive because we want the time to move forward. And then what we want is this to, basically for the quantization so that it's easier, we want the boundary to be preserved. And this translates just say that these two conditions. So one is of course the background p. So both of them are for the background. One is for p. So p tilde must go to infinity, either plus or minus infinity. So the same behavior as p, and we will see in the next slide that it's in that way. And then what we have is that this, of course, if I remember tilde must be 0 when q is 0. So, what happens if we now apply this change of coordinate, if we go from t to t tilde? So what happens is that, if you remember, those are the 0th order and the 1st order variables that we obtain by solving the equation dd over dt equal to 0, so the total derivative of the Dirac observable. So by solving the equation and by equating the two equations both for t and t tilde, we obtain this relation. So these are 0th order, and that's why I say that it was easy to see that p and p tilde were going to infinity. So the limit of p tilde for p that was infinity is still infinity. And then we have this relation. So if you see, it's quite simple, and I think that it's interesting to notice that the relation between the new perturbed variables is actually just a notation from the old ones. And what we have is that the two classical frameworks generate the same physical dynamics of the system, as I said before. So that's mostly what is observable. Okay, so now we have these variables, and we want to quantize our system because that's the whole point, and I will just go quickly through the quantization. But basically, we assume a semi-classical Hamiltonian here, where k here is something that is related to the ordering of operators. And then what happens is that we just need now to change our variables. So this is the Hamiltonian second order that I showed you before. We just need to transform our perturbed variables into operators. So, of course, our Hamiltonian equations will still be the same. The only difference is that now they will be computed with this semi-classical Hamiltonian. So, now our variables are, we can define these operators here, where A and A dot, of course, are the usual creation and manipulation operators. And then our equation of motion in the icon picture will be given by this formula. So, this could be computed analytically, however, this is much work, like too much work. And what we did is, even though it's possible, what we did is we did it numerically. So what you're going to see now are some plots, so our results. So you will see what happened if instead of mu here, we use mu tilde, as I showed you before how we obtain the tilde. So first, I will give you a picture of what a delay function is, because I told you you can choose whatever you want as long as they satisfy the properties that I presented. So we can then choose any family, and we choose this family. So we try with different families, so not sine, for example, exponential or cosine. They still work. It's just to make it simpler. We have one family that depends on the coefficient A, B, C, D, and E. And so varying these coefficients with different numbers, then we selected the three delay functions which have the most interesting behavior. Because some of them could have just really tiny multiplication. But in this case, you see they are quite different. And this black one, the one I called delta 0, is just no delay function. So it's our old t. And all these will be our old t, I said that I applied delta 0. And all these are also the green, the red, and the blue. Those are our new delay function, which will define our t tilde. So, how does the background change now? So, I didn't mention it before, I believe, but we are actually, we chose to work with the bounds. And the reason being that we don't have a singularity, and then it's easy to see how to go from the contraction to the expansion using the bounds, and it's nice, you can see really nice plot in this way. So indeed, this is the background, and we see that we go from, we have a sort of contraction and then an expansion again. So here, for Q or A, as I said, we're working with A as our canonical variable, this means classical limit. And this means quantum, we are in the quantum regime, and this is where the bounds happen. And if you see what happened is that the black line is when we're working with our t. So we didn't change time here. So we have a simple curve here. You see this black one. So nothing unusual, just a simple curve. But as soon as we start to add up to change our time to p tilde, we see that at the bounds, so where the quantum regime or where the quantum perturbation rules, we have that our trajectories are changing. But still at the classical level, they remain the same. And this, we see this behavior the same for the first order. So when we discuss the perturbation. So I will not show you the p, so the conjugate variables of mu, because the plots are basically the same, the idea is the same. But just to give an idea, so here we have the real part of mu as a function and plotted with respect to alpha. So alpha is defined as this, so where a is the scale factor and ab is the scale factor when the bounds happen. Basically, we put it to 1 in this case, and then we solve for alpha, and we have this. And if you're familiar with this is just basically the number of equal that we are using in cosmology. So as you see, we have our perturbation here, and then there are basically the same trajectories here for all different deltas here, so just p, and all the different delta 1, 2, and 3, so for the tildes, the different tildes that we chose. And again, you see that when we approach the zero, so when we approach the bounds, what we have is that some discrepancies start to happen. So this before the bounds, and then we have during the bounds when we have the biggest discrepancy, and then this after the bounds. So after the bounds, the discrepancy, so the difference between the time in our trajectories, they're actually fading away, and our curves are actually converging. And you can see that the perturbation is amplified after the bounds. So this, as is written here, is for k. If you remember, k was part of the argument of sine and cosine in the relation between mu and mu tilde. So we chose 1k, so a quite big k here. However, we did this plot for a different case. It means for different time and for different time scale. And we see that the biggest the k, so the shortest the time scale, the bigger the clock difference is. So you see here, for example, k is equal to 0.01, and you hardly can detect any difference. However, here you can see that the red and green are a bit separated. So those are the plots for different k's. And but you still see this amplification in this oscillation. And another way to see that, so another way to see this amplification, the perturbation, and to see this clock difference is actually if you look at the plot between the real part of mu and the imaginary part of mu. So at the vacuum, when you have the vacuum state, we have a circle, and you can see this circle here. So it is before the bounds. Then this dotted part, so all of this circle is, you cannot see this, but all the circle is dotted line. The dotted line is before, is the negative part. You cannot see it because it's circling around many times, so it looks like it's a like full line. So this is before the bounds, and we have this vacuum state, just a circle. Then the bounds happen, so we're going from the negative value of time to the positive value of time, for example. Remember this k equal to 0.5 just because it was easier to visualize. The other one has a splitting that is so big you cannot see it clearly. But then after the bounds, as we said, the oscillation, they are amplified as you said before. And you can see it here also in the state because the state is squeezed. And this is the squeezed state. So what happened if we change time also in this plot? So what happened is that if we change time, so if we look at this picture again with the different detail that we have, you see that all the state before and the state after, they are the same. So they have the same squeezing. The only thing that is changing is how they go from this vacuum state to the squeezed one. So you see this difference here. And you also can see that they start at the earlier time to diverge. You see when they start to move from the squeezed part to the from the circle part to the squeezed part is at different times. So I think it's really interesting. And again, we can look at this for all different cases. For different time. However, as you can see, again here is amplified. The difference is amplified, and all of these plots they have the same like circle and then squeezed bar, but as I say, you could not really appreciate it as good as with the k equals 0.5 because of the squeeze. Okay, so now that we saw this, we can see my last plot, which I think gives a quite interesting picture of this work. So is the hyperparameter as a function of time. So the hyperparameter here, this gray part, this gray plot that I hope you can all see, even though it's a bit small, is again, as you can see in the legend here, is when we have just t, so no clock change. And you see that it's just a nice, like this butterfly shape, so we go, we just contract and then we expand like nicely. And then it is crossing zero. However, as soon as we start to add different time, we see that the clock, we see that this at the bounce level, so when we have t equal to 0, we see that first of all they start earlier than the 0. You see that there is this like this distance here, or later, and they do different shapes. So we see that also the way in which the universe is contracting and expanding, the way in which the bounce happen is different. However, again, as before, at the classical level we have no difference, even though we are working at the same classical level. So, to conclude my talk, the expectation value of the dynamical variables is invariant under clock transformation away from the bounds, where the behavior of the expectation values becomes classical. So as we saw here, at the background, again, when we have classical behavior, so for example, big value of the scale function, we have that all the trajectory, they converge. And again, in the perturbation level, again, we saw the same behavior. So for symptotically large universes, the dynamical prediction for quantum gravity do not depend on the clock. And I think that is really interesting, and maybe it does not solve the problem of time, but it is a way to say that maybe there is no problem, since at the classical level, it's actually everything converged, or something else to investigate. So thank you for your attention.
Short questions, please.